Imagine you are auditing the universe's matter budget, and you find a problem so large it feels like a typo in reality. Not a rounding error, not a missing decimal. Most of the matter that should be shaping the cosmos is not made of atoms. It does not glow. It does not absorb light. It does not show up in any telescope image. And yet its gravity is written all over the sky. Here is the cleanest way to say it. When you add up all the normal stuff, stars, gas, dust, planets, people, it is only a small fraction of what the universe contains. Roughly 5% is ordinary matter. Roughly 27% is dark matter. The rest is dark energy. The point is the shock. Most of what exists is not the kind of stuff you can touch. Dark matter is the part that acts like missing mass. It behaves like an invisible scaffolding. Without it, galaxies do not make sense. They rotate too fast. They should tear themselves apart. Instead, they hold together as if a huge invisible halo is gripping them. Think of a merry-go-round spinning so fast that the kids should be launched outward. But they do not fly off. They stay locked in place as if an invisible seatbelt is holding them down. That invisible seatbelt is what dark matter is doing. It is not something you see. It is gravity coming from something you cannot. That is why the hunt became so intense. Because for decades, we had a frontrunner, a candidate that looked almost too perfect. The WIMP, the weakly interacting massive particle. The WIMP idea was seductive because it did not just explain dark matter. It fit naturally into the logic of particle physics. If you had a new heavy particle that interacts extremely weakly, then in the early universe, the math can naturally leave behind about the right amount to match what cosmologists infer today. People called this the WIMP miracle, not because it was proven, but because it felt like the universe was handing us a clean, elegant bridge between the smallest scales and the largest. So we went hunting for that particle like it was only a matter of time. And the hunt was not casual. It was extreme. We built detectors so quiet they make space look noisy. We buried them deep underground, close to a mile down, to escape cosmic rays raining from above. We surrounded them with thick shielding. We purified materials until the detector itself would not poison its own search. And we filled them with a target that is almost perfect for catching an ultra-rare collision: liquid xenon. One of the flagship detectors is Lux Zeppelin, LZ, in South Dakota, about 4,850 feet underground. Inside, it is a large pool of ultra-pure liquid xenon, kept cryogenic so it stays liquid. A WIMP would pass through Earth as if the planet were mostly transparent. And once in a very long while, it might strike a xenon nucleus, producing a tiny flash of light and a small electrical signal. Not a dramatic event, a whisper. This is why direct detection was supposed to be the cleanest test. No complicated astrophysics, no uncertain galaxy histories, just a particle, a nucleus, and an instrument. And now comes the uncomfortable part. With years of data, the result has not been a discovery. It has been a tightening silence. These detectors do record events, but when you account for known backgrounds, there is no excess that behaves like classic WIMP dark matter. The simplest, most popular WIMP expectations have been squeezed harder and harder, and the signal keeps not showing up. This is where people start saying WIMPs are dead. That is not quite true, and it matters to say this correctly. What is failing is not the existence of every possible WIMP. What is failing is the most straightforward version of the WIMP story, the one that felt inevitable. The parameter space where WIMPs should have been easiest to find with today's detectors is shrinking fast. And then there is the next wall. As these experiments become more sensitive, they start to see a different kind of particle that absolutely does exist: neutrinos. Neutrinos from the sun, neutrinos from the cosmos, neutrinos that pass through you in huge numbers every second. They rarely interact, but when your detector becomes quiet enough, those rare interactions become your background. This is often called the neutrino floor. A more honest way to think about it is a neutrino fog. Not a hard limit, but a region where dark matter and neutrinos can start to look frustratingly similar unless you invent new ways to tell them apart. So we are in a strange moment. Dark matter is still screaming through gravity in the sky, but our best attempt to touch it directly in the lab is coming up empty. And the background that replaces it is real physics we cannot switch off. So what does that mean? It means one of three things. Option 1. Dark matter is real, and it is a particle, but it is not the classic WIMP we designed these detectors for. It could be lighter, heavier. It could interact in a different way. It could mostly scatter off electrons instead of nuclei. It could hide behind a different kind of interaction that these experiments are not optimized to see. Option 2. Dark matter is real, and it is a particle, but the dark sector is more complicated than one particle with one weak interaction. Maybe it has multiple states. Maybe it has its own forces. Maybe it talks to us through a mediator particle, changing the signal shape and where we should be looking. Option 3. The hardest possibility to say out loud. The missing mass is not a particle at all. The law of gravity might be incomplete in the regime of extremely low accelerations. This is where the story gets even more interesting, because the field does have other candidates, and some of them are deeply weird. One leading alternative is the axion. Axions are not heavy bullets. They are ultralight. So light they behave more like a coherent wave than a particle hit. If a WIMP is a bowling ball, an axion is a fog that fills space. Axions were originally motivated for a different problem in particle physics, and they happen to be an excellent dark matter candidate. But detecting them is a different kind of game. You are not looking for a nuclear recoil flash. You are looking for subtle effects, like a tiny conversion into electromagnetic energy under carefully controlled conditions. Another idea is primordial black holes. Black holes formed not from dying stars, but from density fluctuations in the early universe. A population of small black holes could behave like dark matter. The catch is that this idea is heavily constrained by many observations, so only limited mass ranges remain plausible. And then there is the gravity alternative. MOND, Modified Newtonian Dynamics, proposes that you can explain galaxy rotation curves by changing how gravity behaves at extremely low accelerations. In some galaxy-scale relations, it can look surprisingly effective. But MOND faces serious challenges when you zoom out. It struggles with galaxy clusters, and it struggles with the full cosmological picture, especially the pattern of the cosmic microwave background that the standard dark matter framework fits extremely well. There is also the bullet cluster, a famous collision of galaxy clusters. Most of the normal matter is in hot gas, and in this collision, the gas is slowed and displaced. But the gravitational lensing mass peaks appear separated from that gas, aligned more with the galaxies that pass through. That pattern looks like collisionless mass moving through, exactly what you expect from dark matter. It is a major hurdle for pure modified gravity explanations. Now, some people bring up wide binary stars as a possible test of gravity in a very low acceleration regime. There have been analyses claiming hints consistent with modified gravity, and other analyses arguing those hints weaken or disappear under different data cuts and contamination control. The honest statement is that this line of evidence is debated, not settled. So we are not watching a story where dark matter is vanishing. We are watching a story where one beautifully clean idea is being squeezed, and the universe is forcing us to widen the search. And that brings us to what happens next. The response is not despair. The response is scale. On the direct detection side, the next generation of underground detectors is being designed to be far larger, pushing sensitivity deeper, and also turning into precision neutrino observatories at the same time. On the sky mapping side, a new era is already beginning. Surveys are mapping the cosmic web and measuring weak gravitational lensing at enormous scale. That lensing is a direct tracer of where mass sits, including the invisible mass. These maps can tell us whether dark matter clumps the way cold dark matter predicts, whether it behaves more like a smoother fluid, whether it has self-interactions, and whether small-scale structure matches our simulations or refuses to cooperate. And if the problem is not particles but gravity, the same datasets will squeeze modified gravity theories hard. No more vague ideas. Any alternative must match galaxy rotation curves, lensing, cluster dynamics, and the early universe relic signals all at once. So the silence in underground detectors is not the end of the story. It is a filter. It tells us where dark matter is not, at least not in the simplest form we expected. And null results are not failures. They are the sharpest kind of information. Finding nothing where you expected something forces theory to stop being poetic and start being specific. The real mystery is not whether the universe contains invisible mass. Multiple independent gravitational observations say something is there. The real mystery is what it is. A heavy particle that barely touches us. A light field that behaves like a wave. A dark sector with its own forces. A relic population from the early universe. Or a correction to gravity that only shows itself in the quietest regimes. The universe is still keeping its books. The totals still come out right when you include the unseen. But the ledger is telling us something brutal. The simplest answer was not guaranteed. The most elegant candidate was not entitled to exist. And the deeper we listen, the more it seems the universe is pushing us past the miracle and into the hard part. Because whatever dark matter is, it is not just missing stuff. It is the architecture that decides where galaxies form, how they grow, and why the universe looks the way it does. The detectors are quiet. The maps are getting sharper. The constraints are tightening. And somewhere in that narrowing space between what we see and what we measure, the next era of physics is waiting.